So now we want to take a look at finding this point of diminishing returns by finding any inflection points and then providing an interpretation for what that means. So in example 3, we have a company that introduces a new computer game using TV ads. Survey shows that P% of the target audience buy the game after X ads are broadcast. So what we want to determine essentially is what's the most effective number of ads to run. So we have an equation for that P% below. We want to find the inflection point of the given function and identify when the rate of sales started to taper off. So this is the same function from example 1. We already found that that inflection point occurs at about 33, rounded to the nearest whole number. So then the question is, what does that mean? In this case, it means that the rate of sales started to taper off after 33 ads were broadcast. So going back to that idea of what diminishing returns tells us, we see that greatest increase in sales over that interval from 0 to 33. That's when we're getting our fastest increase. It's increasing the fastest at 33. And then after that, sales continue to increase, but at a slower rate. So we're getting the best return on our ads from that initial run of the first 33 ads. In example 4, we're given an equation that represents revenue in thousands of dollars, and X represents the amount spent on advertising. So again, we're interested in a similar question. What is the best amount to spend on advertising in terms of when we're getting the most return on that investment? So the first thing we want to do is find an inflection point, or any inflection points, for this given function. So we ask Wolfram Alpha for an inflection point for this given function. We get one at x equals 15. And again, we see this idea that as we're spending money on our advertising campaign, we get some very fast growth initially. We hit this point of diminishing returns, and while our revenue continues to increase, that rate of return has slowed down. So we're still making more money, just at a slower rate. So in this case, we have an inflection point at x equals 15, which means revenue will start growing at a slower rate after, since in this case that's in thousands of dollars, after $15,000 has been spent on advertising. So again, keep in mind, we're still making increasing revenue after that. It's just not increasing as quickly as it was during that initial run when prior to and up to spending that $15,000. In example 5, average monthly rent for a 1,000 square foot apartment from 1998 through 2005 can be approximated by the function below, where T is time and years since 1998. We want to find any inflection points and then provide an interpretation for that result. So in this case, we want any inflection points for 1.64 T to the 4th. So we want any inflection points for this function. Oh, and actually I've got a typo in this problem too. There should also be a plus 62.3 t squared added on to that function as it's given in the example, giving us inflection points at 1.02 and 6.16. So this function should be added on to. There should also be a plus 62.3 t squared. And that gives us inflection points at 1.02 and 6.156. So we're asked to identify when the rents were increasing most rapidly. So only one of those is the correct answer. In this case, we have two separate inflection points to choose from. So what we can tell if we look at the graph a little bit more, again, we're looking for when concavity changes from increasing to decreasing. So here we've got values that are increasing and then still increasing but changing to that concave down shape. At our other inflection point, we've already got values that were decreasing. So this value at 6, while it is an inflection point for the function, isn't that point where concavity changes from positive to negative. What we're interested in is this first point that occurs at t equals a little over 1. So rents were increasing most rapidly during the year 1, which means it's 1 year after 1998. So most rapidly in 1999.